Recording has started. Okay, so I'm just going to very quickly have an overview of what we covered last week. Okay, because some of you, while all of you say you have no questions, let's verify. Okay, so last week in pathfinding, right, we talked about why pathfinding is important in games, right? Pathfinding graph industrial shortest path. Okay, so why pathfinding is pretty straightforward, right? You need people to walk from one place to another without getting blocked. Okay, so uh, the most important thing about pathfinding in games is that it's usually done on what is known as a pathfinding graph, and a graph is nothing more than a set of points, known as nodes or vertices, right? And a set of lines connecting the 2 points. Okay, so let me now try to do some. Uh, okay, so a graph is nothing more than a set of points with lines connecting them. Okay, and so these points are called nodes, all right, or vertices, and these lines are called edges or connections. Okay, edges can have weights, like say this one is weight of 10, this one could be weight of 8, right? And uh the weights will represent some measure. Okay, the simplest one is distance lah. The longer the connection, the greater the weight. Okay, so if the nodes are actually geographically accurate, we call this a Cartesian graph. Okay, so C-A-R. I cannot write with my mouse. Okay, a Cartesian graph is one where all the nodes are in the correct position. Okay, so the geographical location of the nodes actually means something. But in general, graphs are just points with lines connecting them. Okay. In addition, right, edges can have direction. So you can have, in this example, we have an edge going from node A to node B with weight 8, and we might have another edge going from node B to node A, maybe weight 7. All right. So um, as you can see, a graph is quite flexible. It can represent a lot of different things, right? It can represent maps. It can represent family trees. It can represent various things lah. Okay. And if your job is to find the shortest path, right? The starting algorithm that we tend to use is called Dijkstra's algorithm. Okay, which is something that we will cover. Okay, so how do I clear? Um, I should probably have tried this before. Uh, what is the best way to clear? Delete all annotations. Okay, right. Okay, any questions so far? Can So you all know what a graph is. I assume all of you can see my annotation Okay, good. All right. So for example, in this case, right, if you have this map from World of Warcraft, from Warcraft, you might have a pathfinding graph, something like this. Okay, so in the actual game, it is invisible. But the NPCs or the mobs that do the pathfinding to find the shortest path to certain areas, they will follow these edges, the nodes and edges of this graph. Okay, so how do you implement a graph? Right? In our implementation, right, we have a class called graph, and inside the graph there's going to be a list of connections, which we call connections. Okay, and inside graph we have one method called get connections. Let me use the pen. Okay. Oops. Still getting used to the interface. Hold on. Okay, we have one called get connections. All right. So get connections will essentially, if I have this graph, okay, uh, say like this, okay, and I have a graph that goes something like this. All right, and then maybe another one here. Okay, if I'm looking for get connections from node A, okay, then it will return this connection, right? But not this one. But not this one. Okay, because get connections will only return nodes where the node that you specify, in this case the node A, okay, is the from node, is the origin node, right? Okay, then the information that I need in a node, in a connection, is essentially which is the origin node, the from node, which is the to node, and the cost. So if the cost is in this case 6, right, then the cost will be 6 here. All right. Okay. Now, if you look at it carefully, right, all you need for a graph is just the list of connections. But very often you would also want to contain more information about the nodes themselves. So if the node, say this node represents Toa Payoh, right? Okay, Toa Payoh. I'm just having fun writing with my mouse. Okay, and then maybe this node represents Bradle or Bishan, right? Okay, so what happens is if I have a struct, right, a structure called node, okay, a structure called node, it might have a name, right, and this I can store the name Toa Payoh or Bishan inside. Okay, it might have coordinates, right, 0, 7, or it might have a position on the screen if it's a Cartesian graph, and so on. Okay, but strictly speaking, for Dijkstra's algorithm to work, you do not need the node structure. Okay, that is why later on when you see the algorithm, there is no node structure inside the algorithm. Okay, so this is just a review from previously. Okay, all right. Now, essentially, the standard algorithm for Dijkstra is to find the shortest path. Okay. Before I continue, any questions? Can I? 5, 4, 3, 2, 1. Okay. Now, so what happens for Dijkstra's algorithm is that it searches every node and updates the shortest path found to that node so far. Okay, and what it does is it finds the shortest path from the start node to all nodes actually, or at least until it finds the shortest path to the destination node. So how the algorithm works is actually pretty straightforward. Okay, I skipped this slide. Okay, so at the start, what happens is that the start node's cost is 0, and the cost is essentially the cost of the shortest path found so far. And we assume that to get from the start node to the start node, you don't move, and so the cost is 0. And all the other nodes' cost we set to infinity. Then we put the start node in the open list. Okay, so if the start node is A, the start node will be inside the open list. Okay, and this is my open list. Alright, while the open list is not empty, you will get the node in the open list to the lowest cost. So at this point, right, since there is only the start node inside the open list, you will retrieve the start node. Okay, and that is the current node that you're working on. Okay, but later on, if there are various nodes, like say we have A, B, C, right? Okay, you will need to use some algorithm, okay, to choose the node with the open list. Okay, and there is no one standard way to do this. You could use a priority tree. You could use just a normal list and do a sequential search. Okay, but essentially you want to get the node with the lowest cost. If this node happens to be the end node, you're done. You've already found the shortest path. But if not, what happens is that suppose I have a node A, okay, and it currently there is a path that says that it was previously found that it had a path of length 10. But when you come in, right, okay, when you come in, you will check that, oh, maybe the is 8. Okay, I'm explaining this poorly. Okay, so let me put it another way. Okay, so for each connector node, okay, this is okay. Let me reverse. This is not going to look very good in the video. So only for private consumption. Okay, let me undo. Give me a moment. Okay, so suppose I am currently looking at a node A, okay, and this node has an edge going out to at cost 8 with that node B, okay, and previously node B, there was a path that led from node C to node B, okay, that cost 10. All right. Okay, so if this is the case, then what happens is that you see that going from A to B is faster than going from C to B. Okay, therefore I can update this, right? Is the best path found is no longer from C to B at cost 10. It is now from A to B at cost 8. Okay, that's if the new path found is better. If the new path found is not better, you don't update. Okay, right? Then essentially, if this node is not already in the open list, you put it inside the open list. Okay, and then you keep doing that. Okay? Basically, what Dijkstra's algorithm does is it will look for the path with the lowest cost, right? And if so far the node that you are looking at already has been found, right? That means that because none of the edges are negative, okay, then the path that has been found that leads to that node has to be the shortest path. Okay, so it's a bit difficult for me to explain over BCR electronically because it's hard for me to draw. Okay, if you are confused about this, right, come next Tuesday, in class I will go over. I realized that I never actually proved why Dijkstra's algorithm gives the shortest path. Okay, so if you like me to give a informal proof on why Dijkstra's algorithm gives the shortest path, I will provide that on Tuesday. Okay, so this is still the review. We're already 20 minutes in. Okay, any questions so far? Okay, all right, so this is just a review. Let's go on. Okay, and very quickly, in terms of implementation, we will declare a structure called the node record. Okay, and the node record is equivalent to when we say a comma 10, right? Okay, so the node record is for a particular node. So if a to b, right? Okay, and say this, it came from origin node, and this is like 6, this is 6, this is 4. Okay, and as a result, the best route from O to B is from A, and the total is 10. Okay, then essentially this node is a node record for B. The connection is the connection A to B, and the cost so far is 10. Is that alright? Okay, so that's what node record is supposed to signify. Node record corresponds to this. Can? Okay, so with this node record structure, okay, our Dijkstra's algorithm essentially follows the pseudocode that we gave in two slides ago. I won't go through this because you've all coded this in the workshop and you all claim to have completed the workshop, right? In any case, when you whatever the code that you download from Mel gives the solution for last week's workshop. So at the very worst, take a look and try to understand how this one works. Okay, because remember, this week is week 5. So this, yeah. So week 7 we have another quiz. All right. So in a couple of weeks I will be testing you on this. Okay. All right. So this is the algorithm for Dijkstra's. Okay. So and that is a quick review of Dijkstra's algorithm. And we are going into the new topics today. Any questions before I continue? All right. Okay. I assume everybody's all okay. Let's talk about more on pathfinding. Okay. Now, at the end of this lesson, you will learn 2 things. Okay. One is called the A-star algorithm, and the other one is pathfinding on a tile-based map. Okay. The A-star algorithm is essentially an improvement over Dijkstra. Most of the time, it's an improvement. Not all the time. I'll explain what I mean. Okay. And as for a tile-based map, right? So a lot of games, like dungeon crawls, it is a square map. Okay. Or maybe you have a game with a hex map. So the question is, how do I do pathfinding on this tile-based map, right? Without having to construct, say, if it is a 100 by 100 map, without having to construct a pathfinding graph with 100 times 100, 10,000 vertices. Okay, that becomes a little bit difficult. Okay, but the way Dijkstra's and A-star is structured is that you can do it dynamically, and I'll show you that later. Okay, so that's what we're going to do for today. Okay, but first let's talk about the A-star algorithm. There's some issues with Dijkstra's. Okay, the Dijkstra's algorithm is basically designed to solve the what we call the all pairs shortest path problem. Because for a given start node, it actually finds the shortest path to all nodes. Okay, if you take out the part that says if the node that you're considering is the end node, you break. Okay, if you just continue until the end of the open list is completely empty, okay, then what you found is the shortest path from the origin node to all nodes. Okay, and this is a bit wasteful if you're looking for the shortest path to only a specific node. Okay, we do save a bit of time by stopping the algorithm when the end node is the current node, but we can do better. Okay, so take a look at this diagram here. So let's assume that this one is the start. Okay, so say this one is the start node, right? And then when you start looking for Dijkstra's algorithm, okay, you're trying to get to this goal. Okay, so usually you'll take a start node, you'll find it's connected to here, it's connected to here, it's connected to here, and then you'll search along this way, right? Okay, now what happens, and as it goes towards the goal, no problems. It searches all of the closed nodes. Okay, but here's the thing. Um, if you look at it, right, it doesn't go directly to the goal. Okay, this will be going directly to the goal. Instead, it also goes this way. So think of it as Dijkstra, the search pattern is constantly getting further and further out. Okay. And you notice, actually, if I can just search this portion of the graph, right? If I can somehow ignore all of these, that would save a lot of time. Okay, so that's the basic idea of Dijkstra. The issue with Dijkstra is that it solves all path shortest path. If you want to find all path shortest path, then yeah, no problem. You can search. Let me undo this one again. Okay, so if you are doing all pairs, right, it's okay to keep searching everything because you want to search the entire graph anyway. But if you're looking for shortest path from start to the end, I want to, as far as possible, ignore, say, everything from here. Okay, because these things, these nodes will never be part of the shortest path. It is very unlikely that the shortest path goes all the way around to come out. It's always better to be a more direct route. Is that alright? Okay, so that's the issue with Dijkstra. We're trying to find the shortest path between a start and a goal. Okay, and this is the observation that A star is trying to take advantage of. Okay, so how does A star work? Okay, all A star does is that it adds a heuristic that is used to get an estimated total cost. Now the word heuristic is just a fancy term for rule of thumb. Okay, it's a fake rule. It's an approximation. Okay, and what happens is that instead of, if you recall, right, in Dijkstra's algorithm you have a cost. Okay, and every iteration, the algorithm will find the node with the lowest cost, and this cost is the actual cost. Okay, instead we're going to say we don't just want to do the cost, we do the cost plus just this heuristic. Okay, I think my kids are back. I hope y'all don't mind. Okay, so there might be a bit of background noise. Okay, we want to add this heuristic here. Okay, and the basic idea of the heuristic is that this is going to help us direct our search. Okay, the heuristic estimates the cost from the current node to the end node. Okay, and so our estimated cost is the cost so far plus the heuristic. Okay, and the next node that you choose, okay, is determined by this estimated cost, not by the cost so far. Alright, what we're basically saying is that if you look at this graph, right? Okay, we, instead of just choosing the one with the lowest cost so far, okay, we want to find the one that is most likely to be on the shortest path. Okay, and the heuristic is going to help us to do that. All right. Okay, so does so let me give you an example of a heuristic. Okay, now a heuristic would be, maybe let us say that I want to give the so this is my start. Okay, this is my start. All right, and this is my goal. Okay, right, now if I have, say, this one, the cost is 5. Okay, and then this one the cost is 4. Is that alright? So suppose this is A, this is B, and this is C. Okay. Now Dijkstra is going to choose C to be the next node. Agree? Because its cost is 4, while B the cost is 5. Okay. Okay. Is my son wailing distracting?
What can I do?
You want to say hi? You want to come and say hi?
Me or him?
Both of you. Hey. Okay.
Hello.
In interlude.
Hello.
Hey Quincy.
Say hi.
Say hi. Do you see the? Uh, this is Hi.
No, 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 don't poke, don't
Don't
poke.
poke.
Don't poke. Okay? Yes, Papa is teaching, okay?
Yeah. And that would be right. See lah. Everybody pay attention when my kid is around.
Okay.
Yeah.
How distracting is it if I turn the TV on low?
Give it a try. I hope all of you don't mind. Uh, let me see. Delete all annotation, face image. There's no. I'm just checking to see whether there's a way to undo everything. Okay, I'm gonna delete all annotations on this page. Okay. As I was saying. Okay. Wait. At meantime, let me just check to see if Teachen is back. Is Teachen around? Teachen is not around. Okay. Okay. So let me explain how A-star algorithm works. Okay. So let's assume that we start from A, okay, and we actually want to end here. Okay, this is my exit. This is the objective. Okay. Now, if let's assume this is a Cartesian graph, right? Meaning that the vertices are actually where they are geographically. Okay. Now, if I have A to B, right? Okay, and the cost say is 7, and then A to C, the cost is 4. Okay, what Dijkstra will do is that it will choose C first, because the actual cost of C is 4, the cost so far for C is 4, and the cost so far for B is 7. Okay, but as you can see, it is very unlikely that C will be part of the shortest path. It is much more likely that B is part of the shortest path. Agree? Okay, so now what we will do instead is so that there'll be a lot more vertices lah. So it could be something like this, right? And then C could be something like this, something like this. Okay, it could be something like this. Alright. So what we're going to do is we're going to do a very simple heuristic, which is just the direct shortest distance. Okay, and instead of saying that the cost, so currently, right, for B, okay, the cost is the cost so far is 7. Okay, but instead I want to do a cost plus the heuristic. So what is this heuristic? In this case, the one simple heuristic is what is the direct distance? Okay, what is this distance? Maybe this distance is 10. Okay, then for B, its cost is actually 17. Its estimated cost is actually 17. Okay, but for C, this cost is going to be maybe 20. Okay, the direct distance between C and the endpoint. So if you add 20 and 4, 4 plus the heuristic equals to 4 plus 20. Okay, you get 24. So even though the cost so far for C is 4 and the cost so far for B is 7, if you add the heuristic, and if this heuristic is good, it will say, hey, actually B is more promising than C because its estimated cost is 17 and the estimated cost for C is 24. So let's look at B first. Is that alright? Okay, so that is the idea of A star. Any questions? Who does not understand the idea of A star? Okay, at this point, I do a very quick roll call. Everybody just put a message in the conversation. Okay. All right. I think everybody's listening. Okay, that's good. So, everybody get an idea of how this. Yes, I know. Okay, this is how I know that Xin Yang's actually the person on the other end of this conversation. Okay. Uh, Brandon, are you alright? Okay. I think you got one equal too many. Okay, other than that, so let's talk about A star. Okay, so if you understand the concept of A star, okay, then this is actually quite straightforward. Okay, now, uh, so if you look at it, right, essentially, what's going to happen is this heuristic will estimate the cost from the current node to the end node. Okay, right, it estimates the cost from current node to end node. And for graphs where the distance is approximately the same as the cost, the simplest way uh is to use the what we call the I mean basically the direct distance. Okay, right? So let's take a look at the A star algorithm. Okay, very straightforward. Okay? The only difference is that okay, so the first part initialization is the same as Dijkstra. Okay, right? And so what happens is that you will get the node in the open list with the lowest estimated cost. Previously, it is with the lowest cost so far. Okay, remember the estimated cost is plus the heuristic. Okay, and for each connected node, okay, you update its cost as well as its estimated cost. Okay, and then you put the node in. Essentially, that's the only difference between A star and Dijkstra. Okay, this computation of a heuristic, right, and adding it to your cost such that when you retrieve the next node, it is the one with the lowest estimated cost, not the cost so far. Okay, so all A star does is it changes the ordering of the search. Is that alright? Okay, the rest of it, the updating of the cost and the previous node, and then retrieving the path and reversing it, the rest of it exactly the same. Okay, so which means that you need to add a estimated cost here, right? An additional attribute inside a node record. Okay. Other than that, the algorithm is pretty much the same. Okay. You will initialize the so all of this is in Dijkstra. You add this extra line. Okay. And so what is this heuristic? The heuristic depends on your is on a case by case basis. Okay. But like I said, the simplest one is just you just take the position minus the other position, find the length. Alright? All of this is identical. Okay. But the get smallest will return the element with the lowest estimated cost, not the one with the lowest cost. Okay. And then the rest of the algorithm is essentially identical. Okay. So once again, every time you update, you need to update the estimated cost as well. Alright. Uh, I know this is going a little bit fast and a little bit abstract, but during the workshop, you'll get a chance to try it out. Right. Okay. So the rest of it, essentially, you include the estimated cost. Okay. So, right. So there's additional step. Okay. So now the question is, the rest of the algorithm is the same. Okay. Now, so the question is A star worthwhile? Is it worth calculating the heuristic? Okay. And practice has shown that in most cases, or at least in many cases, the answer is yes. Right? Because if you look at, I go back to the diagram. Okay, I'm going to remove all these annotations. Okay, if you look at this diagram, if you based on this graph, is a Dijkstra is going to see all of these nodes in black, right? Okay, and you see the nodes you can barely see it lah. The nodes in gray, okay, those are the ones that have been inside the open list, but because I reached the goal, I didn't continue searching it. So it's actually quite a lot. But if you were doing using A star and the cost is say proportional, the cost of every edge is proportional to its actual distance, geographical distance, then the number of nodes that you will find, you search is probably only around this many. Okay, and then the question really is, how long does it take for you to compute the heuristic? If it is fast for you to compute the heuristic, then yes, this will be much faster. Okay, and the number of nodes that you search will be less. Okay, right. Okay, so let's discuss this, right? Okay, first thing I want to say is, if the heuristic underestimates, okay, then A star will always return the shortest path. When I say the heuristic underestimates, what I mean is that if the actual value, okay, if say the distance between A and B, okay, say the shortest path between A and B is actually like that, okay, and say it's 4 and 5 and 3, okay, right? So the actual shortest path is 12, okay. If the heuristic for A to B, right, whatever the heuristic returns, is never higher than 12, then it will always return the actual value, okay. The which means that if it is if the shortest path is, if the heuristic is always less than the actual value, then the shortest path algorithm, the A star algorithm, will always return the correct solution, okay. And such a heuristic we call it an admissible heuristic. Okay, the reason this is true is because if the actual cost is 12 and the heuristic say returns 10, okay, then it will never return something that is, you'll never, the current cost will never be higher than its actual cost when it's retrieved from the open list. At that point, you will calculate its actual cost. Does that make sense? Okay, if this doesn't make sense, okay, I can go over it again on Tuesday. Okay, it's easier for me to explain on the whiteboard, okay, than here. But that is the basic idea, right? Just remember, if the heuristic underestimates, okay, meaning it never returns a value higher than actual value, A star will give you the actual shortest path. Okay? And if this heuristic is very accurate, then A star could be much better. But if the heuristic is not very accurate, oh, Lawrence has just left. Did Lawrence just rage quit? I shall re-invite him. Lawrence, are you back?
Yes.
Okay, so everything alright? Can okay. So now like I said, if the heuristic is very accurate, in other words, if the actual cost is 12 and heuristic gives me 11.7 or something like that, okay, and it consistently gives me very accurate estimates, then the running time could be much better than Dijkstra's because it will search very very few nodes, okay. But if it takes a long time to calculate the heuristic, or this heuristic, the estimation is very bad, it always returns 1 or 2, okay, right, then A star may actually perform worse. It may actually take longer. Okay? So it depends. A lot of this of using A star is the art of designing a proper heuristic function that you can calculate very quickly. Okay. Now, sometimes you it might be desirable to have a heuristic that can overestimate. Okay, in other words, it's an inadmissible heuristic. Okay, sometimes this heuristic, the actual cost is 12, it may return 13. Okay, then A star may return a solution that is not optimal. Okay, but this may be okay if, as a result, this heuristic is super fast to calculate. Okay, and it's not so bad. You don't always have to find the absolute shortest path. You can just find a short enough path. Then it is possible to use an inadmissible heuristic for A star. It depends on your game. It depends on your problem. Okay, right? So to ensure that A star returns an optimal solution, okay, you can actually check if the current path is better than if the connected node is in the closed list, right? You can check if the current path is better than what's recorded. If so, you remove it from a closed list. In other words, you kick it out of the closed list, right? So remember, in the original Dijkstra, if the node that we're finding is inside a closed list, we assume that it is already done, okay? And then we never check it again. But if you're using an inadmissible heuristic, you can't assume that. If it's inside the closed list, you check if it was better. if the current path is actually better than what's recorded, you remove it from a closed list, put it back in the open list. Okay, in other words, I need to recheck. But this increases the running time lah. Okay, so that's a trade-off. Is that okay? I won't be surprised if some of you are a little bit confused. Do you want me to repeat this part? Okay, so let me go back one slide and let's talk about this one about admissible heuristics, because I think this one is quite crucial uh to understand. Okay, so if you recall, right, for A star, okay, the next node that you check is cost plus heuristic. Cost plus heuristic. Okay, now, here's a very simple observation. If you are already at the destination node, okay, you're already then the additional cost to a destination node, the heuristic should return 0, right? Okay, because this is the actual cost. I'm already at destination node. The heuristic should return 0 because I'm already there. Okay, now if the if the actual, so let's just say we have A, okay, and we are going to B, okay, say the actual cost is 7, okay, if the heuristic never returns higher than 7, okay, that means that when A is in the open list, right, when A is in the open list and something else is also inside the open list, okay, the cost of A will never be higher than 7, okay, because the heuristic is only 7. Okay, I ignore the cost of everything else before. Okay, so I'm just saying that the additional cost of adding A to the path found so far, okay, the additional cost is the heuristic, and if the heuristic always underestimates, then the additional cost will never be 7. Okay, will never be higher than 7. Is that alright? Okay, now once if A becomes the current thing that we're looking at, A becomes the current thing we're looking at, then we calculate the actual cost, which means that the cost plus H will never be higher than the actual cost if H is admissible. Does that make sense? Does that make sense? Okay. Therefore, remember that you only quit the algorithm when the end node is the one with the actual cost. So at this point, if you retrieve the end node, okay, you will always recalculate the actual cost. Okay, you will never end before you find a better solution to the end node. Okay, therefore, if it's the heuristic is admissible, did someone mute me? Someone is being annoying. Someone is trying to yes, you can mute other people. Please do not right click on my video and click mute. Remember, this one is Skype for business. Everybody in the conversation is supposed to have equal. It's not a controller thing. Is that alright? Did someone do it by accident? Okay, so does everybody understand the thing about admissible heuristic? Okay, who does not understand? Okay, okay, if you don't understand or you're still confused, I will review this on Tuesday. It's alright, I think I do have to go on. Okay, so but the basic idea, here's the cool thing lah, right? This gives you a little bit of control over how you design your A star algorithm. Okay, if the objective of your game, right, of finding the shortest path, is to do it as fast as possible, because I got a lot of paths to search. Okay, uh, then you might come up with a quick and dirty heuristic, okay, that may be fast to compute, but may sometimes overestimate. If that is the case, and in certain games and certain problems that is the case, right, then you will find a solution, okay, that may overestimate a little bit. Okay, the amount that you overestimate is based on how far over the actual cost your heuristic returns. Okay. Sometimes it may be worthwhile, then you do it that way. Okay, so a lot of using A star is testing, try and error. It depends on the input graph and so on. Okay, so that is our A star. Any questions? Okay, now here are a couple of things to think about. Alright, now if the heuristic always returns 0, okay, so my heuristic function just says return 0, then your estimated cost, remember, your estimated cost is equals to the actual cost plus the heuristic. So if your heuristic always returns 0, then your estimated cost equals actual cost. That is the same as the express algorithm. Right. So now, finally, the last point I want to make is, when do you use A star? You do it when you can quickly compute a good heuristic. Okay. If it is hard for you to compute a good heuristic, if the heuristic is super inaccurate, or it takes a long time to compute, then it may not be worthwhile. Okay. But for most game problems, especially those on a map, where the cost of moving from one node to another is related to the geographical positions of the nodes. Okay, then there are very simple heuristics you can use. Okay, like just finding the direct, the straight line distance between the two, the two nodes. Okay, that would give it's very fast to compute. It always underestimates because the shortest path between 2 points is always a straight line. Okay, and it always underestimates. Okay, right? Okay, so in your workshop you will get a chance to code your own A star algorithm. Is that alright? Any questions? It's not that difficult. If you understand Dijkstra, A star is just a short half a step forward. My daughter's looking at me. Okay, so any questions before I continue to non-graph pathfinding? In other words, on the top map. Okay, at okay, so Joa is asking, in order to know if it's accurate, you need to test it out? Not really. Okay, you do need to have a little bit of computer science knowledge, and you need to understand how your graph is configured. Okay, so for example, right? Let me just go back. Okay, so for example, if I have a graph that is, if the cost of if this cost is actually equal to the actual distance, so maybe this actual distance is 4, this actual distance is 5, okay, and my heuristic just says okay, so maybe this one is another 5. Okay, if my heuristic just says what is the actual distance between these two, you know that it can never this distance can never be higher than 4 plus 5 plus 5. Okay, you know that from the properties of the graph. It is hard to test a heuristic. Okay, so a heuristic can be proven to be admissible because we know the shortest path between two lines, between 2 points is the straight line. So if my heuristic is a straight line, then no path can be shorter than that. Okay, so we know that that one is admissible. Alright, another one, say, suppose I have a square graph, right? A graph that when all the vertices are like this. Okay, maybe it's like this. Okay, and say every single edge, right, the weight must be at least 1. Okay, say this one is 2, this one is 5, this one is 3 or whatever. Okay, so if I want to find the have an estimate between A and B, right, it's actually quite hard for me, right, because this could be 4, this could be 2, this could be 17 or whatever. Okay, I don't know in this particular graph. So one possible heuristic, which I don't know how useful it is, but it is admissible heuristic, is to say, okay, I'm just going to count 1, 2, 3. Okay, right? So since every edge is at least 1, I know that that the distance between A and B must be at least 3. So that is another heuristic for this kind of graph. Is it a good heuristic? Don't know. That one you gotta test it out. Okay, but we know there's an admissible heuristic. Does that make sense? Okay, AI is not an easy topic. There aren't any hard and fast laws that you go through usually. Okay, a lot of it is about design. Okay, so case by case basis, when you're coding your own game, or when you are doing a program looking for a shortest path, it is important for you to understand the characteristics of your data, characteristics of the graph that you're trying to search. Okay, then you can design a good heuristic. It could be that for your particular graph there is no good heuristic. Then you might as well just use Dijkstra instead of wasting time to calculate a poor heuristic using A star. Okay, so a lot of it has to do with experience and practice and understanding how these algorithms work. Okay, at this point I'm just introducing to you the basic concept of A star. The actual implementation, there's a lot of art to it. There's a lot of practice to it. Okay. Any questions? Okay, so if no questions, you notice I'm now at slide 32 of 34. Okay, so I'm just let me just double check what's the next. Okay, so this is the last slide. This is the last slide, and we're less than an hour in. I will talk to you about this, and then I will give an overview of the workshop they need to do. Okay, please try to spend at either you complete the workshops or spend the next 2 hours trying. Okay, on Tuesday I will come back and review. Okay, please don't do the usual thing of, oh, lesson over, on Tuesday Mr. Un will be giving the answers anyway, right? If you haven't worked on the program, quite likely you won't be able to follow my explanation. Okay, so spend some time, minimum the next 2 hours, or if you're really good, you can complete it before that. That's fine. Okay, working on the workshop. Okay, so so the last slide I want to talk about is that you can actually use the A-star algorithm and the Dijkstra's algorithm to work on a tile map. Okay, so what's a tile map? Tile map is basically if you have a map, something like this lah. Okay, it is just like this. Okay, maybe my character is here. This is my character. Okay, and then there's a rock here. Alright, and then there's mud here or whatever. Okay, right, and I want to find the shortest path here. Okay, so one way I can do it is I can create a graph, right? Explicitly create a graph like that represents the top map. Okay, something like this. Okay, so every node represents a square, and every edge represents two adjacent squares. Okay, moving from two adjacent squares. So suppose this is on grass, this is on grass, right? Suppose this is on grass and this is on grass. Okay, and this node represents this square. Okay, and to move from this square over to this square, it takes one movement point. Okay, then the weight of this will be 1. Okay, and usually it is going to be the same the same movement cost either from A to B or B to A. So if you go the other way, it's also 1. Alright? Okay. So I can construct this graph. Okay. So in this case, it's going to be a 5 times 1, 2, 3, 5 times 5, 25 node graph. Okay. Beforehand, then I just implement Dijkstra's on it or A star on it. Okay. And you'll be able to do the find the shortest path. Okay, but it's kind of wasteful. Right. The main thing is that, so you can see each tile is a node that's connected to its 8 adjacent tiles. I assume that you can move diagonally. Okay, you can move from here to here. The trick is that you do not have to explicitly create the graph. All you need to do is you can calculate the adjacent tiles and the movement cost on the fly. Okay. The last thing, so how does this work? The basic idea is that if you have a, let me see. Okay, the big this is the key, the get connections, right? Um, in an actual graph, what happens is that if you have a node and then it is connected to three other nodes, right? Okay, get connections will return you the all the connections. Okay, these three connections that's connected to this current node A. But if it's a tile graph, get connections will be smart enough to calculate. Okay, for all of the squares, the 8 squares adjacent, what is the cost? Generate the connections for you and then return that list on the fly. Okay, without having to create the graph beforehand. Right? And your workshop, I think it's called 5B. Okay, will give you a practice on it. Are you alright? Then the rest of it is actually exactly the same. Okay. Last observation, what I say is that A star tends to be far superior to the extra. Okay, because it is a tile map, then it is usually based on distance, and you just do a very simple estimation heuristic. You should be able to uh, do much better than the extra. Okay, and in the workshop you will see an example. Okay, any questions? All right, everybody, all right? Okay, so in this lecture, we learned about A star. We talked about admissible and inadmissible heuristics. Okay, admissible is basically heuristics that always underestimate. Inadmissible are those heuristics that may sometimes overestimate. Okay, and then we talk about pathfinding on a tile-based map. It's only one slide. The You will learn this mainly from the workshop. Okay, so what I'm going to do, I'll end the slide here. All right. As usual, is we are using essentially one textbook for this lesson, AI for games, right? And after this, you can work on your workshops. Okay. So what I'm going to do next is going to show you what to expect for your workshops. All right. Okay. So how do I end slide? Um, I have no idea how to stop. Oh, okay. Stop presenting. Stop presenting. Or should I present? Let's present desktop. Okay, I am presenting a desktop. Let me check and see how this works. It is loading. Okay. Having some technical difficulties. Hang on. Okay, can you all see my desktop? I have my. Let me see. An error occurred in presentation. Nope, can't see. Loading. Yes, can see now. Okay. Let me just check. Uh. All right. Where was I? Okay. This week 5. Okay, can you all see my desktop? Can't see? Can see? Can't see. Okay, let me try one more time. Yes, Mickey Mouse on the background. Copyrighted. Error occurred. I can't seem to present the my desktop. There's an error that has occurred. Okay, can you see my desktop? No. Okay, I don't think we can do the desktop sharing. There's something wrong. There's something wrong with the desktop sharing. Okay, so I think at this point, right, I will just have to talk through it verbally lah. Okay, we have. Let me see what I can do. Present programs. Present. Mm, okay, I think I'll just talk through this. Okay, if you take a look at your mail folders, right? Okay, you should see two projects. Okay, the first one is A star. Under A star, you should see a file called Dijkstra grid graph. Okay, and that gives you the solution to last week's workshop. T-shirt's awake now. I'll try to add him in. You do realize that it's a 1 o'clock lesson PM, right? Welcome, Tishan. You have missed the lesson. Okay, but it's recorded. I will put it up probably on mail. I'll put it up somewhere. Okay, I'll notify all of you. Tishan, can you hear me? Yes, it's Mickey Mouse in the background. Okay, so I already went through the lesson. It's recorded. Um, I will try to put it up somewhere. It's not very high quality. At this stage, I intended to put it up on YouTube, but put it privately shared, maybe. We'll see what happens. We'll see what happens. Okay. Uh, but okay. Essentially, what you need to know is that okay. So this is a 3 hour lesson. Officially, I have you guys until 4. Okay. But I would like you all to work on the workshops on your own. Okay. So the first thing you will see is A star, a folder called A star. But inside the folder called A star is Dijkstra. Okay, Dijkstra grid graph, and Dijkstra grid graph should be uh the answer to workshop 4 from last week. Okay, so workshop 5A is A star algorithm. So if you take a look at the document, you should see that you are supposed to take the code from week 4, okay, rename it as A star grid graph, okay, and then change it to the A star version. Okay, so there's some code snippets that um you're supposed to enter in, right, type in, and then try to figure out how to do the uh A star algorithm, right? And then essentially all I'm really asking you all to do is to modify the heuristic function to return the straight line distance, which is also known as Euclidean distance, between the current node and the end node. Okay, so give it a try. It's not too difficult. If you can't get it to work on Tuesday, I will show you how it is done. It's a simple 5-minute explanation. All right. Okay, so that's one thing. Okay, the second thing that you're supposed to do is there's this thing called tile map. Right, I wish I could show it to you, but all you need to do is it says Pathfinding tile map student, right? Okay, when you run it, you will see a character that looks a little bit familiar. Okay, and it does the shortest path on a tile map. Okay, so play around with that and then follow the workshop, and that should be that's should be able to finish both of these in 2 hours. Okay, any issues? Okay, because if there are no issues, what I'll probably do is I'll end the lesson here. Okay, I know it's 1 hour 15 minutes out of a 3 hour lesson. Okay, but there are some limitations to doing this in BCR, and we will try to work around it lah. Okay. You want to see you want to see my kids or something? You want to have a tour of my house? No? Wow. Yeah, my wife is maybe next time. Maybe next time. But Karen, you want to come and say hi? This is my daughter Karen. And can you see? Okay. And that would be Quincy.
Wave at the computer. Wave at the computer, Quincy.
Whoa! High five.
Okay.
Hi. Okay, and that's that. All right. Okay, so that's the end of the lesson. I will see all. Do both workshops. I will see all of you on Tuesday. Are there any final questions? All right. Do the workshop. Work through it. If you got questions, please don't send it here or onto this conversation. Just use the WhatsApp group. Okay. And then we will because WhatsApp, I think we're all very familiar with it. Okay, so please go ahead and use it even though it says GPN 2K17. Okay, any other questions? Okay, if not, I will end the meeting. Okay, on the count of three. 1, 2, 3. Okay, bye bye, see you all next week.